Good morning, everybody. Sorry I couldn't be with you today. I'm around. I'm in the building. I just have a meeting today, so I will be around after school if you want to come in to ask any questions, to reassess, to get help. So feel free to come by then. Today, we're going to do a little bit more with implicit differentiation. I asked you to do those 5 problems last night. Those are going to come into play here at the end. But I want to show you a few more examples, get you a clearly defined process for implicit differentiation, and to work on some applications today. So if you see down here at the bottom of the screen, these are the 2 things we're working on, sort of how we've broken up all of our rules so far. Implicit differentiation, that's what we were doing yesterday. That's what these examples are going to be over. Just I give you a relationship containing x and y variables. Can you take the derivative of it and get dy dx by itself? Straightforward. Can you do the skill? And then applications, that's going to be the applications. Can you find where the tangent line is horizontal? Things like that. To be honest, the applications here, once again, are fairly similar to the applications that we've been doing with all of the different differentiation rules. So that's something that's not really changing. All right, so let's go ahead. Hopefully you've gotten your notes out by now and you're ready to go. All right, this right here is a set of steps. Implicit differentiation is one of the most formulaic things that we are going to do this semester. So it really is useful to know these steps because they are the same every time. For that first standard, I believe, yeah, standard 10, the implicit differentiation, where you're actually just doing it. If you know these steps and practice them, you're going to get a 4 on that. You're going to know exactly what to do every time. So first of all, we take the derivative of both sides with respect to x. That's number 1 right here. We know how to do that. That's not the hard part. Now the second part, this is a part that you might not have thought of. You need to move all of the terms with dy dx to one side. This says the left-hand side. That will work. And move all of the other terms to the right-hand side of the equation. So in order to do that, after you take the derivative, you might need to distribute things out. Basically, you want to get rid of parentheses. You want to expand things as much as you can after you take the derivative so that you can move your dy dx terms to one side and your other terms without dy dx to the other side. And then we factor dy dx out of all those terms on the left-hand side. That's why we need to have every single term over there has a dy dx, so we can pull one out of each of those terms. I like to describe it as undistributing dy dx. So you want to have a dy dx in each one, and then you pull it out front. And one way you can check yourself is to look, if I distributed this dy dx back in, would I get back to where I was in the previous step? So pull it out, write what you think the factoring is going to be, and then check. If I distributed this dy dx back in, would I get back to where I was in the previous step? Next, we want to solve for dy dx. That means get dy dx by itself by dividing both sides of the equation by the left-hand factor that does not contain dy dx. So that's whatever's left over. When we pull that dy dx out, we'll have dy dx and then a big set of parentheses times a whole bunch of stuff. We want to divide all that stuff over to the other side. If the sub could please pause the video now so that everybody can finish copying this before we go on, that'd be great. All right, going through a few examples. Both of these examples have the same instructions up here, find dy dx. Just like we talked about yesterday, we're assuming that y is a function of x. So we have x cubed minus 3x squared y plus 4xy squared equals 12. And the first step, looking back at what we just wrote down from the previous page, was to differentiate both sides with respect to x. So ddx of both sides. So it might even be a good idea to write it out like that, ddx of both sides. So this lets us know exactly what we're going to do. Now if we look at this right-hand side, the derivative here of a constant by itself, is 0. So we know that. And then our derivative on our left-hand side, if we look, we have 3 separate terms here, split by addition and subtraction. We know that the derivative splits over that, so if we can do d dx of x cubed, then we can do d dx of 3x squared y. We can treat each of these as their own individual problems. So for the first one here, it's going to be real straightforward. For the second one, hopefully we realize, oh, we've got a product here. That's why this is underlined. And then for the third one, oh, we've got a product again. So I'm going to go ahead and show that right here. So the first one, x cubed, that just becomes 3x squared. And then when we do 3x squared y, the 3 can just go along for the ride, and then it becomes 2x times y. So 3 times 2x times y gives us 6xy. And then the 3 goes along for the ride here, and x squared stays the same, and we do the derivative of y with respect to x, so dy dx. So that's how we do the product rule there. Now we had to be super careful here that this negative went along with both of these two. It distributed to both parts of the product rule. Okay, same thing here. The 4, if you notice, is in both terms here. And we do the derivative of the first one, derivative of x, nothing there, a 1, great, times the original second, y squared, 4 times y squared, plus, and then our 4 is still there, the first one, x, times the derivative of the second, the derivative of y squared. And we're like, oh no, derivative of y squared, I have to do some chain rule. So the outside is being squared, so that's where we get 2y, and then times the derivative of the inside, dy dx. So that's how we get this right here. Now, how many terms here have a dy dx in them? We already have everything expanded out. Nice. This term right here, no dy dx. This term, no dy dx. This one does, and this one does as well. These parentheses right here are not meaningful at all. These are not multiple terms. This is one thing. It's 4x times 2y times dy dx. So this is going to become 8xy dy dx. So we got these two terms that need to stay here on the left-hand side, and the rest of this stuff, we're going to move it to the right-hand side. So we move all that stuff over to the right-hand side, just like this, and then we factor a dy dx out of the remaining terms over here on the left-hand side. Now we're just trying to get dy dx by itself, so finally all we have to do is take all this stuff on the left-hand side that's times dy dx and divide it over to the right-hand side. And there, right there, is our final answer. The steps that we're following here are exactly the same each and every time we go through this process. The only thing that's going to change is that we notice here we had a product rule, and then we had to do chain rule because we had y squared. Here we just had a product rule. We didn't have to do chain rule. Here we just had a regular old derivative. Nothing fancy going on there. Here we just had a derivative of a constant. The only thing that changes each time is us figuring out what derivative rules do we need to apply in what order. If the sub could pause the video here to give people a minute to finish copying things down before we go on, that'd be great. Okay, one more example here. Same instructions, let's find dy dx. So we're going to take the derivative with respect to x of both sides. So I'm going to go ahead and write that out. That lets me know exactly what I'm doing. If I look on the left-hand side here, derivative with respect to x of x, well, that's real straightforward. That's just 1. And then I look on the right-hand side, I see I've got y times secant of 5 over y. So that's going to be a product rule right there, y times secant of 5 over y. So I'm going to need to use the product rule. So left-hand side, I just get 1. Let's go through this right-hand side together. So derivative of the first, derivative of y with respect to y, or with respect to x, I'm sorry, dy dx. Derivative of the first right there times the original second, secant of 5 over y, plus, that's in our product rule, the first, which is just y, then times the derivative of the second. So I need to take the derivative of secant of 5 over y. That's not going to be easy. So what I need to do is realize that this is a chain rule. I've got an outside function, secant, and then I've got some stuff plugged into it, 5 over y. So derivative of secant, secant tangent, that's the derivative of the outside. Plug in the old inside, 5 over y, multiplied by the derivative of the inside here. Now the derivative of the inside, I'm going to get up for a second. I might get a little quieter so I can write something. Derivative of the inside actually is another chain rule. We need to rewrite this first. So we rewrite this up here, and we realize that what this is 5y to the negative first. This is 5y to the negative first. So we're going to need to take the derivative of the outside here. 5 is a constant multiple. The 5 just goes along for the ride. So here we've got 5 going along for the ride, and then the derivative of the outside. I'm going to need a little more space than this. So I'm going to move this a little bit. We got 5y to the negative first. And when we take our derivative, the 5 is a constant multiple. It just goes along for the ride. 5. And then we've got this y, which remember is a function of x, all raised to the negative first. So we need chain rule. So we do the chain rule. -1 times something to the -1 minus 1. We subtract 1 from the power. -2. So that's a derivative of the outside right there. Plug in the old inside. Plug in y. And then times the derivative of the inside. Times the derivative of the inside. dy dx. So that right there is how we get this final term here in the derivative. -5 over y squared. So here's the -1 times 5, -5. And y to the negative second, well, we can move that to the bottom to get -5 over y squared times dy dx. That's a little tricky one right there. But we could have also done that or also found that using the quotient rule. But if you recall, it's a lot easier to rewrite these things when they're just a single number on top as bringing the bottom up to the top so we can use the chain rule. Okay, now let's look at where our dy dx's are. This right here is all one term. That has a dy dx. This here is y times secant of some stuff, times tangent of some stuff, times all this stuff. So this is one term with a dy dx. So those are our two terms on the right-hand side. They both have a dy dx in them. And this on the left-hand side does not have a dy dx in them. We already have our terms separated on the right, on the correct sides. I mean, we have the dy dx's on the right and the non-dy dx terms on the left, but that shouldn't matter. So we can factor a dy dx out of this first term right here, and a dy dx out of this second term right here, this big whole thing. So we go ahead and do that, and we've got this right here. So if you notice right here, I did a little simplifying. This whole term, it's all multiplied together, so the order doesn't matter. I have y times -5 over y squared, so here's one y on top and a y squared on bottom. So I went ahead and combined those into a -5 over just a single y on the bottom. Just a little simplifying thing right there. And once we're right here, the rest of this process is fairly simple. We've got dy dx times all this stuff. We're trying to get dy dx by itself, so we divide all that stuff over to the other side. The process here, as hopefully you're starting to see, remains the same each time. The only hard part is going to be knowing which of your derivative rules to use in what order. So really going back to standard 8, going back to when we were doing product rule, quotient rule, chain rule, all those problems together, this is the same exact thing, only now we're doing it with y's and x's together instead of just with x's. It is the same exact idea. All right, if the sub wants to pause the video here real quick so that everyone can make sure they have everything copied down, that would be fantastic. All right, any time remaining, there's a worksheet over applications. As you go through that worksheet, you will realize that each problem on that worksheet corresponds to one of the 5 problems I asked you to take the derivative of last night. So at the top of those, it'll even tell you exactly what dy dx should equal for those 5 problems you did last night. So that is your answer key for your work from last night. If you did not get those ones solved correctly, this is a good time for you to go back and see if you can apply what you've learned today to fix that and compare the answer that for dy dx that you get to what the application worksheet says you should have gotten. Tomorrow we'll continue to work on the applications, and we'll do more practice with implicitly differentiating. The applications, some of them they're difficult. They're going to make you think. You do not need to finish the whole thing for tomorrow. I recommend that you try to get through at least a couple of the examples, at least 2 or 3 of them. Each of them has their own page, and they ask you questions, a lot of them about tangent lines and slope and things like that. Once again, if you have any questions, feel free to come in and see me after school. Hope everybody has a good rest of their day, and thank you.